So welcome to UT Energy Symposium for February 25th, 2020. Our topic today is smart decarbonization of the built environment in the nexus of climate change, population growth, and technology adoption. Our guest speaker is Dr. Juliana Felkner. She's an associate professor in the School of Architecture here at UT. Welcome. And this is describing one of the 11 projects and teams that were selected by the Energy Institute's call for proposals organized around the core theme of fueling a sustainable energy transition. And this is an interesting project in that it's not only School of Architecture, but it's got the Cockrell School involved, leaders there, College of Natural Sciences, and LBJ School. So your research and teaching addresses societal challenges that come with increasing urbanization of the world. So thank you for being here. We look forward to your presentation.
Thank you very much for the introduction. Thank you everybody for attending. It's good to see you all. So today I'm going to talk about how we can look at decarbonization of the built environment, especially in the case of Austin. I will cover a few projects that we've been working on. The first one is going to look at the impact of climate change in Austin in years to come at the building level. So we're going to first look at retrofitting buildings and how do we make them more energy efficient and what will be the impact of that in the long term. The next project will build upon the first one, and it's looking more at the larger scale. What will happen if we think about densification in Austin in order to deal with our increasing population growth and also in view of increasing temperatures. How will we deal with that? So we simulate a few different scenarios that I will show you all. And then I will also talk a little bit about my teaching because we address these with our students in architecture, specifically looking at how do we add vertical extensions to historic buildings. So anytime you densify, you don't want to destroy your culture of your cities. So how could we add density without sacrificing our heritage? And then finally in the outlook, I will cover what we plan to do with the project that's been funded by the Energy Institute. The motivation for this research is mainly because 34% of U.S. greenhouse gas emissions are due to the built environment. So we have a lot of impact on the environment, and the IPCC has noted that the decarbonization potential in the built environment could be up to 90%. So this 34%, when you combine it also with the other, let's say 30% is transportation and roughly another 33% is industry. If you look at transportation and buildings combined, that's basically our cities. So how we design and build our cities is over half of the CO2 emissions. And so we have a lot of leverage as designers, urban planners, architects, engineers to address this issue. So the first project I'd like to talk to you about is the impact of climate change and envelope retrofit on urban energy consumption, comfort, and overheating in Austin. So what we did is first we took a specific neighborhood in Austin. We wanted to look at West Campus because West Campus is already undergoing so much change, so it's a good test case for what could happen in Austin to come. And we wanted to look at 4 different housing types. In green, you see single family residences. In blue, you can see the multifamily. Yellow is office and red is retail. So this area is already becoming mixed use, where you will see a juxtaposition of different building types from single family homes to retail and larger multifamily homes. And then on the outskirts of this area, you see still very many original single-family homes, and of course offices and retail among the major streets. So the first case, we wanted to look at what if none of the buildings had any kind of refurbishments. So their insulation was left the same, their window types were left the same, and we modeled this into the year 2100, where we were also taking into consideration the estimates for temperature increases during this time. And you can see the black dots represent each individual building. So these are all of the buildings in West Campus modeled. The gray is 50% of buildings, and the black line is the median. So without refurbishment, you can see that our energy use for all buildings will increase over time. However, this is not really realistic to think about all of our existing buildings lasting into 2100 without any refurbishment. So next we looked at what happens when we do start to refurbish our buildings. And here we tested just improving the wall material, and this looks at starting or finishing all refurbishments by 2040. So that's why you can see it levels off after that, even with temperature increases, because all refurbishments were done by the state. You can see the shadow line of the gray. This is representing if you had no, these are the old ones that were not refurbished. So this is to give you a comparison. And you can see also the existing median line from the non-refurbished buildings. So you do start to see quite a bit of energy savings if you refurbish just your wall materials. If you improve the glazing or the windows of your building, you see even more of a dramatic improvement. So we think this is because we are a cooling dominant climate where we rely upon a lot of air conditioning and we have a lot of sun. So refurbishing those windows is going to improve the performance a great deal for your energy. And best of all, we found if you changed both the walls and the windows in all of the buildings, you could see the energy consumed by all buildings would be much lower than the median, even what we have today, even in the face of increased temperatures. So we could have a huge impact on our carbon emissions just by refurbishing our buildings, both windows and walls. However, we wanted to think what happens in the case of a blackout, which we might start to see more and more of in the future with extreme weather events. And so here we modeled first the reference case. This is in 2018. You could see mean high indoor temperatures in Celsius. In the case of a blackout, your indoor temperatures for retail, which is shown as red, could get up to 104. The blue represents multifamily housing. So these perform the best, we think, because they're insulating each other and there's a lower window to wall ratio. If you look into 2100, with no refurbishment, you can see that temperatures can get up to 112 inside retail and up to 104 in single-family houses, which are in green. If you look at the refurbished case, where you refurbish all the windows, all the walls, in 2100, we're going to see, if you see that little green dot up there, that's representing a single-family house, above 112 degrees indoors. Retail, also above that. Most of the single-family houses would be around 108 degrees inside without air conditioning during a blackout. And even the multifamily homes, which are pretty well insulated from each other or from the outside, would still reach temperatures of 104. So this also can be seen as not only if there's a blackout, but also for some of the more vulnerable populations, people who cannot afford to pay their energy bills. It's important to note that these temperatures are very dangerous, as are these, especially for older and younger people or anyone with health problems. So that's a good question, yeah. Yeah, that's the buildings are just spread out more vertically because of the temperature changes. But that's a good point. You can see now that different building types are going to respond differently to an overheating condition. And that was somewhat surprising to us. We thought that they'd somewhat be affected in a similar way, but you can see the retail is having the worst case. The no refurbishment case, if we don't refurbish our buildings, they'll start to consume 67% more energy just for cooling by 2100. So that's not something necessarily we would want. We're trying to reduce our carbon footprint, not increase it. Full refurbishment of windows and doors will decrease our energy use by 13% by 2040. So that's a step in the right direction in terms of energy savings. However, it is important to be aware of the risks. So refurbished building envelopes will create more disastrous overheating conditions, even with natural ventilation. So we even looked at what if you have naturally ventilated buildings? Will that help some of this phenomenon? But it didn't. It was still, we were still seeing mean indoor temperatures above 41 degrees Celsius by 2100 if you had a blackout. And it's also interesting that different building types will experience this in different ways. So there's a lot more research to be done in this area, and our group is starting to look at this issue along with other groups on campus, mainly for Austin, because that's where we are and that's what we care about. We're using Austin as a test case, which of course can be relevant for the rest of the country as well. So building upon this first study, we were thinking about Austin. We're growing so rapidly. How do we deal with all of the new people coming in and the increased population in general? You can see in the last 100 years, Austin's skyline has changed dramatically. Even in the last 10 years, it's changed quite a bit. Our traffic has gotten a lot worse. So planners are starting to really worry, what are we going to do? And so we started to look at this in terms of also climate change. How will we deal on the larger city scale with this issue? So this project, Urban Densification and Housing Typology for Climate Change Mitigation, is looking at the larger scale effects of how we're going to address climate change and where we should densify and what timeline should we densify. It's a very tricky subject. There's a lot of not in my backyard, which is totally understandable. On the other hand, we don't want to have more sprawl either and more traffic or nobody really wants to have a high carbon footprint from driving so far to work each day. But some people just don't have an alternative. They simply cannot afford to live close in. So we're looking at different densification scenarios. And again, we took West Campus. We wanted to do a growth model and look at what if each of these plots could be parametrically modeled to see the impact of its growth over time. And so for a single parcel of land, you can imagine right now in many parts of West Campus, what you see is this scenario where you have about 4 single family homes on a single parcel. And other parts of West Campus, you start to see more of this situation where you've got about 3-story low-rise buildings. Often this is student housing, but not always. There can be other people living in these as well. And slowly you're starting to even see a few of these mid-rise buildings, which are about 8 stories and higher. And here we classify the tower as being anything over 24 stories. And again, we project far into the future. We looked again into the year, up to the year 2100 to imagine how will Austin look by then. And this is how we modeled it. So if you look first at the colors, we represent single family with the gray, the low rise with the orange, mid rise with the pink, and the tower with the purple. And we ran many different scenarios to try to get an idea of what it might be like if Austin grows one way or another. And we thought about the population growth predicted by the city, for the city as a whole, and we scaled that down to just think of West Campus if it grows in that same way. So in order to do that, for West Campus to continue to contain that much growth within its borders, this is what we found. In order to occupy that amount of land and deal with the increased density, by 2090, almost all of it, if you mix mid-rise and tower, almost all of those gray single-family homes would be squeezed out. So we're trying to model different ways to see how could we have more green space, how could we not have every single-family home phased out, but also how do we deal with the increasing population. We also considered the temperatures. So this is by the IPCC. We used a moderate projection. So the estimate we used was A1B scenario, where they're expecting temperature increases of between 2 and 3 degrees Celsius. This is a moderate one. We might change it out later on to think of the more extreme case, but this is a moderate case that supposes kind of a mix of fuel types by 2100. So not completely phasing out fossil fuels, but having a mix. Of course, we don't know what will happen by then, but that's our assumption. And when we look at these different models, we wanted to think about what would be the energy demand combined with housing growth scenarios up until 2100. And what we can see here, this is the ground area energy consumption. So how much energy is consumed. This is the timeline, so this goes up to 2100. And here you can see the population in thousands. And then this is the energy expected based on the A1B IPCC scenario. So you can see it's going up very dramatically. And this is typical median year for temperature. And this is the residents. So population will increase. What you see here is that the gray represents single-family houses. Imagine we had mostly these. And slowly, with the orange, you start to see more low-rise houses taking up those parcels. Pretty soon, we're not going to, if we lock ourselves into low-rise houses on those lots, pretty soon, by 2060, I believe, or no, 2040, there won't be any more land left. So West Campus could not grow anymore after that point if you decided to only build with this housing type. If you decided to just stay with single family, there's not enough room in West Campus to go beyond 2030 with our current growth. If you look at only mid-rise, you see single-family homes can continue to make up a portion of those plots, And even up till 2070, if you have mid-rise mixed with some single family, that would still work. If you only do towers on those lots, so one tower you can see is replacing a whole lot, so 4 single family homes. Yeah, it would be a pity that those 4 homes are lost, but if you think of it in terms of all of the homes that would not be lost, if you do take up one block with the tower, you can see almost half of your parcels could still be single-family homes with green space. So this will have an impact how we grow, both on outdoor climate, such as urban heat island effect, ventilation, shading. There are a lot of different impacts that we haven't modeled yet that will be important to consider as we grow. What we did consider is the energy growth based on, or energy increase based on these increasing temperatures. And you can see all scenarios do see an increase of energy use in time. However, compared to mixed development where we would allow all types of development, so all types is what we imagine could happen, that slowly they start to mix all types, a little bit of low rise, a little bit of mid rise, a little bit of high rise, something kind of like a mixed checkerboard. That type would not help as much with the energy savings as if you did the 2, what we would consider densest options, which are either mid-rise or tower. When we modeled the energy use of mid-rise only or tower only, we can see annual energy use difference. You can save quite a bit of energy from tower housing only. Also, some from mid-rise, so this is almost 5% savings. This is about 12% savings by 2040, 2060. It would definitely help because, again, we think they're insulating each other. So here we see the energy use impact of climate change on different urban densification strategies. You can see by 2040 there won't be a lot of room for these 3-story buildings. They would most likely be torn down and rebuilt, which is also a consideration when you think about the embodied energy that goes into the construction of these buildings. So cooling load will increase regardless of housing type. So in all cases, multifamily housing would greatly reduce the cooling load per capita compared to single-family housing, which is what we expected. Of course, the adverse effects of climate change, weather, will increase over time as warming intensifies, no matter how we build. But it's important to note that half of the increased energy use will be due to population growth, but the other half is going to be just because of increased temperatures. So now I'll talk about something a little more optimistic. This is some of my student work. So in class, I teach both construction, which is kind of their applied structures class, and environmental controls, which is where they consider the energy use in their buildings. And I give them a combined project for both classes where they can think about how to absorb the increasing population in Austin without losing our heritage buildings. So a lot of the students I teach are from Texas, some are from Austin, and I ask them what is their impression of some of the historic buildings downtown, even though there may be only 1 or 2 stories and developers tend to think nothing of tearing them down. And I was really surprised about the connection that some of the people have with these buildings. They get very emotional about them and they know them and they've grown up around them. So it is part of the heritage. And so it's an interesting and kind of a personal goal of theirs as architects to think how to preserve that. So we look at all kinds of examples of vertical extensions for historic structures. Part of this is to give them a lesson in structures, but the bigger lesson is how do they think about densifying historic areas, which Austin has. And you can see many examples from extreme towers added to historic buildings or just subtle additions made to buildings. And I take them through quite a few different precedents throughout the world that they can look at and be inspired by. And one of the characteristics of adding on to historic buildings is that normally the addition is meant to be contrasting so that there's no kind of false advertising that, this was always this way. So the historic preservationists like there typically to be a contrast. If you are going to add something on to it, that it's not confused to be part of the original, because the original should still be legible. So you can see in this single family house here, this row house, they've added just a single story. That's a moderate addition, but then you can see in other places they've added almost twice the square footage. Here's another example I like to show the students. These are actual built projects where you can see they've even preserved the state of decay, because that's part of their history, and just built within it without disrupting it. And another thing that I try to stress with them is to think about this condition walking along the building, looking up at it. So some of these precedents, like this one, this is in New York. This is where you're walking on the street. Let's say you look up at, this was a project by Foster. If you look up at this, you won't even really see the tower, because you'll be so close along the facade, you'll really only see the historic building. It's only if you get far away, like the camera person in this case did, that you'll actually even notice the tower. And so in some places, even Seoul, Korea, I've heard that this is common to do, and they'll simply have a setback so that your eye level won't even see the addition. So sometimes it can be subtle, even though it's adding a lot of square footage. So this is one building in Austin that some students wanted to add an addition to, and the reason is they liked the history of it. It was designed in 1938, and they liked that it had already been added to, so it was already added. It had 8 stories to begin with, and it had a 9th story added in 1949, and then they added a 10th story in 1952. And now it's listed on the National Register of Historic Places. And the area they saw a lot of potential for, without disrupting the building itself, was this parking garage behind it. They didn't propose to get rid of parking, even though it's a question, what will we do with parking in the future? Instead, they just wanted to build on top of it and still allow natural lighting to get into these windows on this side. They weren't too worried about blocking a view from this, since it was office, not residential. So their intervention was really sensitive. They looked at the wind flow, orientation, solar gains, and here's their structural model. So you can see everything. This is the original building. They design over a parking garage, these additional stories, and then they bridge to the original building as well. So they're trying to tread lightly on the site while still adding residential space. And here they are defending their projects. We have, of course, engineers come and give their critique about their solutions, as well as planners. So it's always interesting to see how it's accepted by other disciplines. This is another example. You can see here they have an old historic building that they didn't want to really intervene too much with, but yet they wanted to add more than twice, 4 times as much capacity. So they followed their columns along the existing column grid of this structure, but it wouldn't have held it because historic structures are normally not over-designed too much. Maybe you can add 1 or 2 stories, but not a whole lot more. So we've taught them different solutions where you can go right alongside the existing columns so that you don't interrupt the floor space or the existing occupancy below. And then you can even wrap those additional columns so that they still look like one. So you can kind of slide by the existing columns within the structure without disturbing it and without trying to calculate would it hold it up or not. And that's what they did here. I do this even though I would call this project that I do with the students a little bit controversial, especially with the historic preservationists in our department, well, in our school, because it's touchy. Again, it's the not in my backyard mentality. If you love a historic structure, you don't want to see it messed with, but we're trying to think of how can you save them from being torn down? And that's what developers more and more are doing. And this is one solution, although some of the solutions are a little bit radical that the students come up with. We encourage them to kind of stretch their creativity. And I always stress to them, the structure will have a life of 80 to 100 years, sometimes more. The longer you can stretch that out, the better from an energy point of view, because there's a lot of energy that goes into tearing down and building up a new building. But that means you've got to retrofit it, you've got to take care of it, you've got to allow for flexibility, changes of use over time. So we teach them a lot about adaptive reuse. And we also impress upon them the importance of the HVAC system. That normally just has a lifetime of 15 to 20 years, and the efficiencies of those are critical to how much energy your building will actually use. So to achieve net carbon zero by 2050, which is a goal that many cities are hoping for, every building that's either built or retrofitted today really counts. So you don't want to lock yourself in with a building that you're going to tear down in 15 years. You want to really plan for the future and do it the right way, which is part of what we're looking at with this new project funded by the Energy Institute. It's a new interdisciplinary project. We're working with people from the Cockrell School of Engineering, the LBJ School, and we're looking how to combine issues of urban planning, urban energy modeling, smart algorithms, and policy into different scenarios that we can create for, in this case, we're looking at Austin again. So first we want to develop an agent-based simulation framework that will study urban energy models under various climate scenario projections. So building upon past work and seeing where we can go deeper into that, but also incorporate more ideas of urban planning that will be, because of the link with the policy specialist, we can start to see what is actually realistic for the zoning and for issues of equity. Also for policy development and uptake in terms of technology diffusion or retrofits. How do policymakers help out with this situation? So let's say you want to go with solar on your house. How can they make that more affordable for people? Or what if you want to retrofit your house, but you're a renter and you don't have that power? What kind of incentives could be given to the landlords? And the most technical part is from the engineers in the group. This is artificial intelligence for advanced intelligent energy management. This is what I think is really novel about this project. Here you can see the team. This is Dr. Zoltan Nagy, who's in the audience. You can also ask him questions after about this project. And he's also part of the whole community's whole health, Bridging Barriers initiative. And then myself from architecture, Peter Stone, who's in natural sciences and is also part of the good systems. And then Adriana Beck, she's in the LBJ school. also she's focusing on policy, not only business. And this is from the AI specialist, Dr. Nagy's work, looking at how we could start to model realistically energy in Austin. So here you can see the orange represents the grid distribution, energy, communication is in blue. And then of course, this is very typical of Austin, many single family homes. What if photovoltaics start to take off? They already are in some neighborhoods. So this is 2020. What about storage? How do we store this energy? Looking at the larger scale. And then finally, what are the role of smart appliances for reducing your overall energy use, not just at the building level, but overall at the urban level. Then he modeled into 2040, 2060, 2080. You can see that these buildings start to communicate with each other. They start to store each other's energy. Maybe even they become less vulnerable to power outages. Energy you can see here from a photovoltaic is being stored in a charging station into your vehicle, an electrical vehicle. So it's interesting to imagine this future. It will surely be different than that first image I showed you of Austin 100 years ago. No one knows exactly what it'll look like, but we're trying to model to have the best case scenarios for our future. So now I'd like to open it up for questions. Thank you very much. Yes.
Did I see that right on one of the first, well, it wasn't one of the first slides, but it was a while back. You had a slide about the increased air conditioning load, and it wasn't just all the way out to 2080. You had a 2030 that, if I was reading that right, yeah, I think you just went past it. Go forward, unless, yeah, that one. Mm-hmm. Does that mean you expect we'll have 40% higher cooling load in 10 years?
So which bar are you looking at in 2030?
Well, 2030, right. And all of them are roughly at 40%. I'm not sure what is that? Can you interpret this slide for me? What does this mean?
So, okay, this is cooling load increase according to the A1B scenario. So this is assuming a moderate 2 to 5 degree Celsius increase, not by 2030, but by 2100. But this is based on this slow increase in temperatures from the IPCC. And yes, it is seeing an increase of 40% for cooling.
And
for all buildings.
And this does not, that would entirely be global warming, or half of that is population increase and half is climate change?
Right, half of that is population.
Okay.
Very good. I should have written that on the slide. Half will be population growth, half will be from the increased temperatures.
So just to make sure I'm getting it right, if I tell somebody that at least according to this model and A1, if you use A1B, in 10 years, we will have to use 20% more energy to cool the same amount of space.
Yes, that's what our models are showing.
Have you talked to anybody at ERCOT? We might want to set up that meeting. I don't think they've seen this. That's pretty stunning, right? I mean, because half the cooling load on a summer day, half of our load on a summer day is air conditioning. Maybe a little less, but about half. So 35, 40 gigawatts. So you're talking about 10 extra gigawatts of load because of climate change.
Yeah.
And solar panels and storage, but I don't think this made it into their long-term system assessment. It probably should be. Sorry, thanks.
No, that's a very good question. We are trying to get data from Austin Energy, and also we've been advised to talk to ERCOT. It is hard to get their models exactly, but it would be nice to share our own with them and have a talk. That's a good point.
Well, so in speaking in resources, particularly this is electricity, but I think about the other parts of infrastructure, and I would love to be in some of these meetings when the city is, like the water department, for example, wastewater. The pipes that used to serve an area, they're too small anymore, and that is a huge undertaking to replace all of that. Now we have these, I think densification makes a lot of sense, but my gosh, I just see all these towers going up, and
Yeah.
there's hundreds of new living areas. What kind of load it's putting on in the water, and of course electricity
Yeah.
as well. How is that being dealt with? Are we having conversations, UT, with that aspect? And
Yeah, the infrastructure is a big issue. So that's something where we'd like to look in the future. Of course, anytime you densify, you're going to intensify your water treatment and possibly have to increase your pipe capacity. We compare that when we look at running those pipes all the way out to past Pflugerville or farther. And it's far more efficient, actually, to deal with it in a dense way than to start to also build roads, any kind of infrastructure farther out. It's that distance that's taking up a lot more resources than working within your city, well, let's say downtown limits, and retrofitting your existing infrastructure there. So we do think that in terms of the embodied energy of the materials themselves and the construction, that it would be less to work in a denser way within the city. But of course, you are going to have more people whose water you're going to treat, and you will have to account for that. But we have some initial calculations that will be far less than if you have that same amount of people in multiple new power treatment or water treatment plants elsewhere. So that's something that we have someone who's looking a lot at infrastructure. I think Fernanda Lici in the Cockrell School of Engineering is specializing a lot in that, and that is very important to think of. And Adriana, one of our other collaborators on this project from the Energy Institute, we don't have her picture, but we're working on it. She's very good about thinking about all of these different infrastructure scenarios anytime you build a new area. Even though she's a policy expert, they've already got data on some of these issues. So that's a very good question. Yes?
Let me ask a quick question. I'm wondering if there are any kind of miracle technologies or materials on the horizon that developers or builders are holding off on in terms of cost. Like, is there any kind of waiting game of not moving on this yet because people expect some new solution to come out? Or is it really just a matter of design at this point? Does that question make sense?
It does. It makes perfect sense. I've been waiting for innovations in air conditioning. I know Dr. Nagy works a lot with air conditioning and HVAC systems, and we have a student also in our sustainable design program who's an engineer, but he's in the architecture department trying to look at new ways of developing dehumidification techniques for air conditioning. If someone could solve that, we could save so much energy with air conditioning. But so far, yeah, it seems we can send a man to the moon, but we should be able to innovate with air conditioning. That's one area where we would have a huge impact. I don't know where that's going at the moment, though. Hopefully soon. Yes?
Well, this was next, right?
Yes. Do you ever get a diseconomy of scale with your towers? For instance, you have the Austonian downtown. Is that even more efficient? And is there some level which you start wasting energy because it's too high?
Yeah, that's a good question. I've read about, there is one paper I read that's looking at what is the optimal height of buildings in terms of energy use. They often look at the floor area, though, and I think it's more important to look at per capita in order to really address the real issue. There's also been a study by a PhD student in the Community and Regional Planning program here at UT who looked at the tax base. So what is the tax revenue you can get off your building and what is the optimal density? So he mapped out some places in Austin that he saw ripe for growth, moderate growth, just adding a few stories, but his was based completely on economics, which is not my area of expertise, but it's why I'm glad we have Adriana Beck on board because she's more in this area of economics, which in the end drives everything, doesn't it? Nothing gets built unless it's profitable. So I have to learn myself how to work more in those constraints. That's a good point. Yes?
The other gentleman who pointed out the problems with infrastructure improvements to accommodate this kind of growth brings up this other question of how do you handle the rainwater that falls on the incredible increase in impervious cover in West Campus, which is right on Shoal Creek. Could you speak to that issue, please?
Yes, that's a big issue. So anytime you densify, it is thought that you do increase the problems with your water treatment because of that impervious cover for parking especially. When we looked at the ones most at risk of causing that problem in our models were the low-rise, so the 3-story, where you have a lot of that surface parking. It's so hard to do underground parking in Austin because of our rock here, but if you look at some of the tower scenarios, for a building that expensive, they would naturally go underground or have some of that parking vertically dealt with. And you could then have green space in the same amount of land. You would get a lot more people in the same amount of land than if you did the low rise, and then you could have more green space theoretically if you did your parking under the tower. The biggest problem is all that surface level parking, which high density naturally starts to squeeze out. But if you do see something like New York, of course you're going to, if you don't have any break from those towers, of course you're going to see more impervious cover than what you would see with the single family houses that have the front yard, the backyard. So now more and more designers, urban designers, are looking at ways to incorporate more green space in order to deal with that. I don't think right now they've solved it properly in West Campus. It's definitely a problem.
Yes, you mentioned blackouts. You were considering the question of blackouts. And, walking up 8 flights is hard.
Yeah.
Walking up 30 flights is,
Yeah.
Impossible for many, many, many people.
Right.
So is anybody taking this into consideration?
That's a very good question. So we see this in Chicago a lot. They're not able to get out in time. Normally they're not even trying though. They're already asleep before they know they're starting to overheat in most of the overheating deaths in Chicago. But that is a good point. How do you access such high levels, and what is the optimal height to deal with that? So it's exactly, if you don't get in your elevators and you've got to go up the stairs and it's hot, that's already a risk scenario. So yeah, you would think they would have to be, in order to be truly resilient, they would have to depend on generators for such cases. There would have to be some kind of scenario where they would not lose power for the elevators. That is a big question. So anytime we look at densifying and making more efficient for energy purposes, we have to think of human health and human safety.
This isn't just, projection. I mean, it happens all over the world.
Yeah.
In the Paris suburbs, France, they've got a lot of 20, 30-story buildings.
Yeah.
And the elevators aren't maintained well enough, especially if it's low rent or public housing. And there are people who are stuck.
Yeah. Yeah, that's a problem. And Paris has had a lot of deaths. They've been hit hard with heat waves. So that's definitely a consideration that I think should be modeled before proposing such high density. How do you deal with getting out? Also in case of fire.
Hi, I'm intrigued by your comments or your introduction about incorporating artificial intelligence into some of these ideas, projects, initiatives. where do you envision that? Is it at the consumer level, the system-wide level, machine learning systems, all of the above?
So I mentioned that that's actually the work of Dr. Nagy, so maybe I'll let him answer that. He's one of our collaborators for the Energy Institute project.
Thank you. For this particular project, we're looking at end-use automation, energy use automation. So when do we store energy, when we release it, especially when we talk about renewable energy integration? Well, in these cases, and how we can shift loads over time, also to address the increase in energy use that we're expecting. And so the basis on this project is that things are moving all the time and things change over time, and so we need the AI systems to adapt to these changes over time, and so that's and on larger scale, and so that's why we're doing it. And
So are there examples out there in the marketplace?
well, I mean, and we chatted before, so things like when you say, when should you charge your electric vehicle when it's cheapest? So do you give signals day ahead? Do you not? But then you start thinking of things like, well, you as a consumer, do you want to every day think about the price ahead and make a decision based on that? And probably not, and that's why we need a system that's doing it automatically for you. And it's the same with if you just use, you know, the renewably generated electricity to charge your domestic hot water tank. Then when do you do that? Things like that. Does that answer your question?
So actually related to that and building on that, one example of AI that's in the market right now is the Nest thermostat. It's not always enabled. A lot of people disable it, but if it's enabled, it could pre-cool a home. So that's, I mean, I'm interested in your thoughts on like how quickly that might scale. Nest thermostats are already in 5 to 10% of homes, something like that. But I'm also interested in the question of the blackouts, and if you had some graphs up there of like, the scatter plot of like how hot it would actually get. So if I'm reading that right, what you're saying is when you refurbish a home, it's going to get hotter inside in these heat waves. And that's just because the envelope is tighter, correct? But you would also be able to hold a set point longer if you pre-cooled. So I guess I'm interested in just general comments on that, but I guess the specific question there, if we're trying to keep this as questions and not commentary, the question would be, did you model anything like that? Like how long could a refurbished home hold that set point through a blackout for a period of 6 or 8 hours instead of only, 20 minutes or something if it's unrefurbished and air is leaking out to the outside? Is that anything you've looked at or would look at?
Yeah, that's a critical point I didn't mention. These are looking at if you had a blackout that occurred more than one day. So if you had a short-term blackout, then it wouldn't be this case. That's true. It would hold the cool air longer. That's a very good point.
That's what confused me.
Yeah.
Thermally better envelope and better windows, you're going to have a great deal of lag in heat transfer.
That's true.
So, okay, so we're saying that model is over several days of no power, not just, okay, that makes sense.
Which we're hoping is not so likely,
Right,
but
okay,
it's all the more reason to think of renewables, so
yeah.
we wouldn't have that. Yeah?
About the green environment for this. In like single family, are you considering the situation for like, you're just looking at housing, but are you looking at what if the house is on a wooded lot? I mean, trees make a significant difference in that. So are you incorporating that into the study of green space, particularly trees in the environment and how they would affect? How you differentiate between no green and green? So
That's a good point, and it is important to consider. We have a PhD student in our Texas Metro Observatory who's starting to map out tree cover, because that also affects shading and humidity. So he's starting to map out where the trees are. That's the first step, knowing in the city where you've got a lot of tree cover. And that is a next level that we'd like to incorporate into the models in order to better understand what's happening in single family, because they're not all going to be as in the drawing, right, where we've shown everything as just having one or two trees. Some have, like in Hyde Park, it's almost like a jungle in places where those houses are very well shaded, and it's also the question, how many trees are you willing to sacrifice? Where do you try to be more sensitive? That's a good point. Once we get the data citywide for where the trees are, he's even looking down to what species of tree. That's one of his research interests. The overheating question, I always took it for granted that tree coverage is good because it shades your house. And I was at a conference recently where two professors started arguing about tree coverage. One was saying, yes, they shade you, and then another was saying, yes, but in a time of a blackout, they're trapping some of the heat and humidity. And so there's debate, and we don't have the models currently, but we want to simulate the conditions that are best for energy conservation through shading, but also allowing, in the case of a blackout, wind to pass through. Mainly it's about ventilation. But that's a good point.
Okay, one other thing concerning the green space, has anybody done any psychological or emotional studies on how these environments affect people where you're cutting out?
Mm-hmm.
Like the West Campus that you were showing, I mean, there was no green space anywhere. I mean,
Yeah.
what kind of impact is that going to have on people?
Yeah, this is something we look at. We have a Professor Wilfred Wang and Dean Almy, who are looking at urban design. And green spaces, it's been found very important to mental health, overall health as well, not just psychological, but overall health. And how do you actually have, so in this image, it looks like there's no green space in the tower. But if we had shown a larger West Campus model, what you would see would be actually a lot of green space surrounding the tower on neighboring lots and just a few towers. So you'd actually get, if we were to do a ratio, you'd have more green space and more people if you had a few towers. The worst is when you have a few low rises all around. They almost always get the trees. They maybe have a small courtyard, but it's usually given to parking. So here you see row after row of these low-rise developments with very little green space, maybe a few trees along the street. And if you compare that to the single-family model, you have a lot less green space overall, not only on that individual parcel, but neighborhood-wide. But the tower, although it's taking up one whole parcel, what we didn't show is that surrounding that would be opportunity for more green space, assuming population growth. So looking into 2100, not today, but into the future, you could have more green space with a tower than less, even though it sounds counterintuitive. And it's also a question, we had one project looking in our School of Architecture at Germany, how do they build around Berlin? And they have a lot of very special forested area. And in Berlin, they also don't want to densify. They want to keep single-family houses close to the city. But if they don't, they're going to lose their forests. And that's another kind of, it's a trade-off. There's no single answer, but if you don't do it in the city, you have to do it somewhere else. For us in Texas, what that means is farmland. We lose some of our farmland for these housing developments. And then we're less independent when it comes to our food.
Can I ask one more question?
We'll come back to you.
First off, thank you so much. So part of the struggle right now is that we are heavily reliant on natural gas and coal-fired power plants, especially during peak hours. Peak hours being, before the sun rises, people are going off to work, and then also when they get back home around 6 p.m. So the sun doesn't really shine, strongly during those times, nor is the wind really blowing at those times. And so has your team done any research to kind of overlay the impact of, let's say, if you could insulate these buildings better, which is part of the reason, as you mentioned, why the towers work pretty well. If you could insulate it to where you're getting more benefit from the times where you're using solar energy to power your home, have you kind of seen what that impact would have, what type of impact that would have on the decreased reliance on, natural gas plants that are more that are more carbon intensive?
Yeah, that's a really good point. So we had one student who was looking at retrofitting, and he looked mainly at the peak energy demand, how to reduce that. There's a lot you can do with pre-cooling at night that works better in not such humid climates. We've got humidity as the issue for our cooling, and also orientation plays a great role. So you don't want to have an afternoon facade that's just open and not shaded. So you don't want to have large windows on your west facade ever, because you're going to get all of that afternoon sun in. And then by the time you come home at night, it'll be almost impossible to get cool without a lot of energy. But how you could plan that with solar, right now it's my understanding when you do have photovoltaics on your roof, you can't use it directly. Is that right, Dr. Nagy? It goes automatically to the grid? Like you can't use your own solar when you want it, so to speak.
That doesn't mean it's just not there. It's not there when you need it. I mean, short-term
Right.
storage can cause it faster.
Perfect. And a quick question on the photovoltaics. Who would implement it and who would own it? Because of course there's a big NIMBY movement. Would the utility companies be the ones implementing and managing it, of course? Or would you have to incentivize owners to do that?
So that's something I think our other colleague Adriana is looking at in the policy department. How do you incentivize it? How do you make it economically realistic for people? I don't think she has the answers yet herself, but that is part of what we're going to look into. Those are very important questions. It's exactly what this project will hopefully answer. Thank you.
Hi, you brought this up in your last answer, but have you thought about incorporating humidity levels into your model? Because that's also a parameter which affects human comfort a lot. And also like the density of humans present in the building, it
Yes.
significantly affects the humidity. So have
Yes.
you like thought about bringing it up in your model?
Yeah, our energy modeling, it deals with dry bulb temperatures. We should add more consideration to the perception of the temperature based on humidity. And right now, even our building codes are designed for northern climates where you want to keep heat in, or else dry climates where you don't have the humidity issue. And even our rules of thumb for passive design come out of places that don't have this issue of humidity. So I'm hoping that more and more students here at UT, especially the student we have coming from Florida who's dealt with humidity all his life, will hopefully find a way to start considering humidity. But when it's not even in our building code sufficiently, it's hard to find it in the modeling software. But that's a good point.
Finish up
Yes.
with one more question.
Yeah. My other concern is water. Where's all the water going to come from to take care of all of these people? And I mean, what brought this up mainly, you mentioned farmland. Right now, I've just read that Austin's looking at taking water from east of town, which is water that farmers use. And so there's this huge discrepancy there about, who's more important for getting the water.
Yeah.
And with the climate change, we have a possibility of extreme drought times. So how are we going to solve all these water problems?
Yeah, that's a good question. So I talked with someone who's in, I think, archaeology, and he's been able to look at the history of the climate, and he's projecting the future. And I spoke with him at a conference, and he said, oh no, we will have drought. It's just going to get more and more intense with the drought. How do we deal with that? I mean, I don't know how much our aquifers can handle. And it's true, there will be equity issues involved with that. Of course, some people do rainwater collection, but the problem is you get a lot of rain at times you don't need it and hardly any. We're starting to see extremes, more rain in the spring, then towards August we're just not getting nearly enough. So I don't have currently a solution to that. We have someone who's really good with water is Catherine Lieberknecht in community and regional planning. She's looking at all the different waterways, and she's on the Planet Texas 2050 project with me, trying to map out water resources throughout the state of Texas. So she'd probably have a better answer than I do, but all I can say is drought is coming, and I don't know how to deal with it.
Well, on that happy note, I'd like to thank our speaker. Thank our speaker very much.
Thank you.